All right, we'll start. So in the last class, we discussed all the polygative properties. We discussed about osmosis, we discussed about reverse osmosis, and we also discussed about osmotic pressure and how osmotic pressure is a polygative property. Okay. Some more information that I want to discuss with you people is about osmosis, related with osmosis. Osmotic pressure, as you remember, when you have a semi-permeable membrane that is existing between pure solvent and solution, and this semi-permeable membrane is allowing the movement of solvent particles via itself towards the solution side, right? Now, this movement can be stopped when you are applying a mechanical pressure on the solution side, right? This pressure, which is capable enough to just stop the movement of solvent particles from the pure solvent side to the solution side, will be known as osmotic pressure. If you are increasing the pressure greater than osmotic pressure, then the solvent particles from the solution side will be moving towards pure solvent side. This process is known as reverse osmosis, right? All of this we discussed in the last class. Now talking about some different solutions, two different solutions. Okay, what about the situation where I have two different solutions? So I would like to show you the scenario first in order for you to understand. Let's say I'm mixing salt in water. Let's say I'm mixing sugar in water. Okay, and what I do, I keep them side by side in a semi-permeable membrane. Okay, so the first solution, that is salt in water, is solution A, that is on the left side. The second solution, that is sugar in water, is solution B, that is on the right side. Okay, so what I want you to understand is that osmosis doesn't care that the other side should be pure solvent side or one side should be solution side, then only it will show the movement. No, basically osmosis is dependent on concentration. So if there is a solution which has less solvent concentration, there is a solution which has more solvent concentration, right? The solution which has more solvent concentration will have the solvent molecules move from its side to the other side if they are both connected via a semi-permeable membrane. Okay, so it really doesn't make any difference whether you have taken pure solvent and connected it with semi-permeable membrane to a solution, or you have taken two different solutions. So basically, if you have two different solutions, A and B, and if I were to say that the solvent concentration, and pay attention to the words, when I say solvent, it's only solvent, it has nothing to do with solute. Okay, the solvent concentration, the amount of solvent of A is greater than the amount of solvent in B, then automatically, and yeah, they are connected via a semi-permeable membrane, then automatically the pure solvent molecules from A would start moving towards B. If the solvent concentration is greater in B compared to the solvent concentration in A, the solvent particles will start moving via semi-permeable membrane from B to A. If there is a situation where the solvent concentration of A and B are exactly equal, right, there will be no movement. Or in other words, if I were to say that if the concentration of the solutions in both the cases is same, there will be no movement. In simple words, if the osmotic pressure of solution A is exactly equal to the osmotic pressure of solution B, then you got two solutions which can be considered as isotonic. Okay, so isotonic, the word refers to the solutions which have the exact same osmotic pressure. When they are connected via a semi-permeable membrane, the movement of solvent particles from either side to the other side will never take place. Okay, all right. If there is a solution which has a greater osmotic pressure compared to the other solution, then the solution which has a greater osmotic pressure will be given the name of hypertonic solution, and the other solution which has a lower osmotic pressure will be given by the name of hypotonic solution. Okay, so these are some terms that you should be remembering. Okay, all right. So isotonic solutions are the two solutions having same osmotic pressure at a given temperature. Hypertonic solution is a solution which has hypotonic. Okay, so hypotonic solution is a solution which has less osmotic pressure than the other solution. Hypertonic solution is a solution which has more osmotic pressure than the other solution, and I think you will understand it this way. The one which is hypertonic would have its solvent molecules moved from its side to the other side, which is hypotonic. Okay, and you should be understanding that the hypertonic and hypotonic solutions are never individually recognized, which means a solution will be hypertonic only when it is connected to a hypotonic solution. A hypotonic solution will only be considered as hypotonic when it is connected to a hypertonic solution. So they are relative to each other. Okay, fine. We're done with the concept of osmosis, reverse osmosis, and everything related to it. Now I would like to move to the next topic, which is about the discrepancies that we observe in colligative properties. Now that comes due to abnormal molecular masses. This part has been deleted from the CBSE syllabus text, but for competitions, it is an important part. So I would like to discuss. What I want you to remember that when we started discussing this chapter, I told you about colligative properties. I gave you the definition of colligative properties, which says that these properties are dependent on the number of solute particles or any participant in the solution, but only on its number, not nature, right? So if these particles are dependent on number, and if I say that while calculating, we are doing mistakes in finding out the total number, then the colligative properties value will also change and we will get a mistake in calculating the final colligative property of the given solution. So first thing is, why do we ever get a mistake, or why is the chance of having a mistake in the first place when we are doing everything right, when we are taking all the values right? So what I want you to understand is that the colligative properties that we are calculating does not consider some simple chemical behavior of these particles or these solute particles in the solution. So because of the ignoring of a behavior from these solute particles, we are getting abnormal molecular masses. When I say abnormal, it's nothing like something out of this world phenomenon. It is actually something we expect, and it doesn't happen that way. That's it. That gives us the meaning of term abnormal. So first of all, let's say I'm calculating the molecular mass of any random solute to be X. Okay. And in the solution, I find that it is not X. Now, if you remember, each and every colligative property could be rearranged in its formula, where you are getting molecular mass at the left hand side and everything at the right hand side. For example, osmotic pressure pi is equal to CRT. C can be written as number of moles upon volume RT. A number of moles can be given as W by molecular mass into V RT. So molecular mass, if it is taken at the left hand side, the colligative property rearranges as molecular mass being equal to given weight upon osmotic pressure multiplied by volume whole multiplied by RT, right? Which means the overall colligative property, or pi in this case, would be changing or would have a discrepancy in its numerical value if capital M, that is molecular mass, is changing, right? So basically each and every colligative property will have some impact on them in terms of their numerical value, right? When there is a change in the molecular mass. Let me just handle the student. Joshua, can you hear me? Joshua? Joshua, this is not your class. This is new 12 standard. Joshua. Okay. So what I was telling you is that every colligative property can be rearranged in such a way that you get a clear relation between the molecular mass of the solute and the colligative property, right? So if the molecular mass is changing, the colligative property will change. Now, coming back to the discussion where I was telling you that the molecular mass will change under certain circumstances. So what are those circumstances? We'll discuss it now. First is association. Second is dissociation. So what about them? See, let's say I have taken benzoic acid in the solution. Okay, benzoic acid happens to be the solute. Now, the fact that I was ignoring while taking benzoic acid as the solute is it dimerizes. What is the meaning of being dimerizes? Actually, two molecules of benzoic acid will connect with each other due to the hydrogen bonds to create one single unit that is also known as dimer, right? I'll repeat it once again. Particularly the case of benzoic acid or ethanoic acid, these carboxylic acids have a property of dimerizing. So what happens during dimerization? Every two molecule that I have taken in the solution in the form of solute will combine with each other to create one single unit that is a packet of two molecules, right? Like it's very simple to understand. um, i gave you let's say there are 20 eggs and I'm giving you a set of 2 eggs 10 times, right? So you understand that each set will be carrying 2 eggs and they are connected somehow. I connect them with a glue, so you will never get a single egg. You will always get 2 eggs connected together, right? In the same way, let's say there are 400 molecules of C6H5OH, but actually the number of particles after 400 and every two in these 400 molecules connecting with each other to create one single dimer unit, the final units that I get is 200, right? I hope you understand this. If I am having 1000 hydrogen atoms and you know that two hydrogen atoms combine together or connect together, bond together to create one molecule of hydrogen, that is H2, the total number of molecules of hydrogen I will get is 500, right? So basically, when I'm taking the colligative property in calculation, the molecular mass I have been taking was actually double of the individual colligative property. I'm sorry, half of the individual colligative property or half of the individual molecular mass. Okay, I will make it very simple and clear for you to understand. See, when I was taking the molecular mass of the given solute in the colligative property, it was M, right? In the situation where I ignored the fact that the molecules are connecting together, but the solution and the colligative property doesn't care that the molecules are connecting together or not. Okay, I mean, it actually cares, but my calculation doesn't care. The colligative property does care. Okay, so what I did, I ignored the fact that the colligative property was considering two molecules or two atoms as one single unit. Okay, two atoms of any given solute which was connecting together to give one single unit, but I considered those two molecules which are connected together as two separate units. So basically, the molecular mass I took was half of the way colligative property is taking the molecular mass of the solute. Okay, in simple words, if I'm taking the molecular mass of C6H5COOH as X, then colligative property is considering the mass of one solute particle as 2x. Because for colligative property, it really doesn't care whether it is benzoic acid or dimer of benzoic acid. It will consider the number. Okay. So if the number is half, automatically the molecular mass doubles. So the molecular mass I have been calculating, okay, would be wrong, because the molecular mass the colligative property is taking into consideration is actually double. Okay, so whatever molecular mass I will be getting, I should half it. I'll repeat it once again. Two molecules of benzoic acid are connected together to give you one dimer of benzoic acid, right? C6H5COH 2 times. Now, the colligative property took 1 unit of C6H5COOH 2 times connected together as one particle. So according to the colligative property and all the depression and freezing point, osmotic pressure, elevation boiling point, relative loading of vapor pressure, whatever value we calculated using the colligative property, it was referring to a molecular mass which was double the actual molecular mass, because we ignored the fact that the molecules are connecting together to create a dimer. And colligative property doesn't care whether it is a dimer or a monomer or a trimer. It will simply count the number of particles and create the change in value of the property. Okay, so whatever value we are calculating is basically on the number, and the number have halved. So automatically the molecular mass have doubled. So the actual molecular mass is half of what we have calculated, because the colligative property took one single unit which has double the mass of the original molecule and gave you the value of the property. Okay, talking about dissociation, there are many different solute particles fondly known as electrolytes, which would never remain in the form of a molecule when they are mixed up in a solution. For example, best example, sodium chloride. It's a very strong electrolyte. Almost 100% of NaCl will dissociate as Na plus and Cl minus. Let's assume it's 100% dissociation, right? So one molecule of NaCl is converting into one Na plus and Cl minus. From where I see as an observer, I added X molecules of NaCl, right? I will give this X a number later, but for time being, let's first understand the idea. So X molecule of NaCl are being converted into obviously X molecules of Na plus and X molecules of Cl minus. Now, there are two situations. One, an observation from my side. Two, the observation from the colligative properties side. Okay, from my side, I added one NaCl molecule and X number of NaCl molecules were added to the solvent to create a solution. The colligative property should be dependent on X number of NaCl molecules. However, this NaCl electrolyte dissociated into X time Na plus and X time Cl minus. So actually in the solution, there are total number of 2x particles, and the colligative property doesn't care that the individual solute particles are molecules intact or ions individually roaming around. It will take one ion as a particle as much as it will take one NaCl molecule as a particle. Particle is a particle, right? Whether it is a molecule or it is an ion, the colligative property doesn't care about it. It will do the final calculation of molecular mass based on as many particles it is obtaining in the solution. That's what the definition of colligative property stands for. It depends only on the number of particles, not the nature. So the value that we will be calculating for the molecular mass would be actually half of, let's assume that Na and Cl for time being have equal masses. Okay, to make our discussion easier, obviously you understand it's not the same, but what we are calculating according to the colligative property would be half of NaCl's total molecular mass. So basically the actual molecular mass of NaCl is twice the value of the molecular mass that we have calculated. Okay. By now, if you haven't understand the relation between how the colligative property calculated gives you the molecular mass half or double of whatever the parent molecule is, it's absolutely fine. If you understood that colligative property value will be different than actual real value based on our assumption and calculation because of molecules dissociating and associating in the solution, then your job is done.